In the first day, we have seen an introduction to the workshop and a primer on geometric algorithms. And due to shortage of time, we could not see the second part, that is a primer on approximation algorithms, which we will see today. So the first part of today's agenda is recap and doubt clearance. So let us quickly recall what we have seen. So we have seen that geometry has many branches, and one of the branches is computational geometry. And many interesting problems that arise in real world can be formulated as a computational geometry problem, and one can design realistic algorithms, practical algorithms for these problems. And if you solve a problem in computational geometry with an algorithm, we call it a geometric algorithm. And when designing a geometric algorithm, one of the primary goals is to minimize the running time of the algorithm so that the implementation is fast. And we have seen a concrete example problem also, which is called the closest pair of points problem. So in this problem, the input consisted of n points on the plane, and our objective was to output the closest pair. We found that there exists a divide and conquer algorithm which can report the closest pair of points in only n log n time. So we spent some time to get to this algorithm, whereas the brute force algorithm is computing the pairwise distance for every pair, and since there are n choose 2 pairs, the running time is order n squared. So the divide and conquer is an improvement over order n squared, right? So far, if you have any questions or doubts, you can ask me on what we have discussed yesterday. Or if you have any feedback to give, you can give me. Otherwise, I will assume that I have done a good job and you understood everything that I said about this algorithm yesterday. Oh, by the way, I have also shared with you an email where there is a nice article on this problem and the divide and conquer algorithm for this problem. So I will encourage you to read this article. It has a very nice illustration along with the code. So if any of you did not receive that email, please let me know.
Are you talking about that medium block?
Median block, yes. I mean, you find the median and divide into 2 parts. And then
not the median one, but then the article is there on the medium. Are you talking about that link?
Medium, yes, yes, that yes, yes. It is in medium.com. That is correct.
Okay, yeah, all right. Fine.
So in case you have not followed anything and you read this article, then things should get clear. Even otherwise, you can ask me later also if you have any doubts. Okay, I think since both recapitulation and doubt clearing is done, so we can move to the first technical session of day 2. All right. So I will move to my laptop and show you some presentation. In fact, we are going to look at this part. So we did not cover a primer on approximation algorithm. First, we will see this talk, which we were supposed to do yesterday. We'll see this now. So what I will do is I will stop sharing. Is the screen visible?
Not yet, sir.
Yeah.
It is visible.
Okay. Let's start the slideshow. So welcome to this talk on a primer on approximation algorithms. So in this talk, I'll try to give you an idea of what is the meaning of approximation and then what is the meaning of an algorithm, which is called an approximation algorithm. So I'll assume that you know what is an algorithm, and then we will see what is an approximation algorithm. So here is a relevant quote. So this is from the British mathematician and philosopher Bertrand Russell. He says, although this may seem a paradox, all exact science is dominated by the idea of approximation. So he says that exact is always illusory. I mean, nothing is really exact in life or in science. Always we have some approximation. Okay, so nobody is an absolute best, nobody is an absolute topper, nobody is anything absolute. It's always some approximation to the absolute best, right? So I like this quote quite much. Okay, let's move on. So what is the meaning of an approximation? So I'll try to motivate the idea of approximation with the help of a real life example. So on the left, you can see the map of our country. And right now, I am sitting in Bangalore, in the southern part of the country. And let us say that I want to go to the northeastern city of Guwahati. So there are many ways I can go to Guwahati from Bengaluru. And let us look at the viable options. So I can take a train from Bangalore. And okay, I have written 50 hours. I mean, 48 will, just a second. later also I kept it 48. Okay, so in this slide there's a typo. I wanted to make it 48. Let's make it 48 so that it helps in our calculation later. Okay, this is good. Now let's go back to the map of India from current slide. Okay, so I'm in Bangalore. I want to go to Guwahati and I have these three options. So if I choose to go by train, it will take at least 48 hours. In fact, it takes about 50 hours, but for the sake of calculation, I'm putting 48. And if I go by, let us say, 3 AC, nowadays it will take 2,500, but for the sake of calculation, I'm saying 2,000. If I go by flight, it will take 3 hours. And if that will take about 8,000 rupees on the average. And if I go by car, then it's even more fantastic. It will take 6 days and it will cost about 30,000 rupees in fuel charges and the cost of the driver. I mean, the wage of the driver. So what do you think is the best travel option for me? What would you do if you had a situation like this?
It seems like it would depend upon what we would like to minimize, uh, the time or the cost.
Exactly. So it depends on what I want to do. What is my goal? So if my budget is only 4,000 rupees, if I have only 4,000 rupees in my bank account, or you know, uh, considering other constraints, if I have only 4,000 rupees, then the other two options, flight and car, are not even viable. So feasibility is an issue. But if I have an urgency, I must go. There is some problem. There is some issue. Then time is a priority factor, and I want to minimize time. And then I should not worry about money so much, and I should take the flight. So clearly, if I have to minimize cost, then the train is the minimum cost option, costing me 2,000 rupees. And if I want to minimize time, then the optimum option is to take the flight because it is the minimum uh, time option. And if I'm not interested in minimizing any of it, then I can just have fun and have a uh, Indian road journey, 6 days, spending 30,000 rupees. Oh, all right. So if my objective is to minimize time, let's take a pointer. If I want to minimize time, but I still take the train, okay? I want to minimize time, but maybe I don't even have 8,000 rupees. So that is a constraint. So because I don't have 8,000 rupees, there is no way I can take the flight. But my objective is still minimizing time. Okay. Then I will say that, okay, I'm going to take 48 hours. Although I could reach Guwahati in 3 hours. So I'm taking 16 times more time than I could have taken optimally. So I'm 16 factor away from the optimum. So the language that I'm going to use now on is that the algorithm of taking the train is a 16 approximation with respect to my objective of minimizing time. If you understood what I said, then look at this data that the car takes 144 hours and I decide to take the car while having the objective of minimizing time, then what approximation have I achieved?
48.
48. How 48?
So 144 divided by 3. So
Okay.
that, yeah. So because the fastest one is taking 3 hours, and I want to minimize time, so I'm approximated by 48 folds.
It is very difficult to write here, but I'm trying to write. Whatever you said is correct, but I just want to understand if 144 by 3 is 48. Let me use a calculator. All right. You're right. So you understand what Mr. Goel said? I think it was Mr. Goel, if I recognize his voice.
Yes, yes.
Okay. So the car would take 48 times more time than the optimal. So we have a 48 approximation. Okay. But we are guaranteed that this is the case. Okay. So with the assumption that the car is not going to take more than 144 hours, and with the assumption that the flight takes at least 3 hours, choosing car for minimizing time will be, in the worst case, 48 factor away from the optimal. All right. So there is a guarantee. So how can we provide this guarantee? We can provide this guarantee because we know beforehand that what is the optimum time that one can achieve to do this job. Okay. So now somebody can tell me what is the, so let us say my objective is to minimize cost and I still take the flight, which is an expensive option. Then what approximation do I achieve?
4.
Why is that?
Because the optimal one is taking 2,000 rupees and where is a flight cost 8,000. So approximated by say 4 folds.
Correct. So if I have confidence that the flight will not take more than 8,000 rupees, and the cheapest option, that is the train, will definitely take at least 2,000 rupees, then I'm at most 4 factor away. So I will be more specific and say that the approximation ratio is at most 4. Of course, you can say it's 4, but you can also say at most 4. So far, so good. So now you understand what is an approximation to a problem at hand. I mean, what is the approximation ratio of the solution given by an algorithm for a given problem. So then the question arises, why do we need to approximate at all when we know how to find the optimal solution? For example, I could have taken the flight if I wanted to minimize time, or I could have taken the train if I wanted to minimize cost. Then let's take the pointer. So why did we have to worry about approximation? When the exact algorithm is available, when the exact solution is available.
So we want to get the solution within the resources available.
Yes.
So yeah.
So the resource is limited. So when multiple resources cannot be optimized simultaneously, then only one resource can be optimized and the other resource cannot be optimized. Right. So for example, if I wanted to get the train, which is taking Okay, so what is, let's say I wanted to get the flight and reach Guwahati as fast as possible. And if I could do it with 2000 rupees only, then I would have been the happiest. But both things cannot be achieved simultaneously. Optimum time and optimum cost cannot be achieved simultaneously. So we have to approximate. Either we have to minimize time and take the flight, or you have to minimize cost and take the train. So another case can arise. Then suppose it is not even possible to find the optimal solution. Okay. So this is a more interesting case. So in this example, we had one algorithm for minimizing time. We also had another algorithm for minimizing cost. But there could be situations where finding the optimum is not even possible. We have no hope of finding the optimal, and then we have to resort to approximation only. Okay. So for algorithmic point of view, this is the most prevalent case where approximation becomes necessary. Okay, now let's move to the whiteboard and see some concrete questions. I'm going to share my iPad screen. If it is visible, you will let me know. Oh, so before I forget, many people have requested for uploading the recordings. So the recordings are like 3 hours long. I have to segregate them into sessions and then I'll upload on the website. But before that, maybe what I can do, I can upload this lecture notes. Why am I not able to share the screen? Just bear with me a minute. Share screen. Is the screen visible?
Yes.
Yes.
Okay. So let's look at a concrete question. All right. So let us say that let us say that there are 3 students. All right. Let us say there are 3 students, S1, S2, and S3. And they sort of work together. They are a group of students working together. And they have a set of tasks to do. So it could be like, let us say, reading papers. So let us say they want to read 6 papers, and these 6 papers are of different difficulty, different level of difficulty, different level of complexity, different length, number of pages are different. So let's say 6 papers. All right. And they want to distribute reading so that everybody don't have to read all the papers. They want to distribute the reading so that later they can meet and discuss, and that way they will be able to minimize the workload, or rather they'll be able to distribute the workload among themselves. Okay. So let us say that the difficulty of reading the paper, or rather I would say the time to read paper 1, or let's say paper I, is denoted by TI. So let us say that the 3 students are almost more or less equally competent and they will take almost equal time to read a given paper. But we know that the papers are of different difficulty, and so one paper may require more time to read, the other paper may require less time to read, but we know more or less accurately that which paper will take how much time to read. Okay, so let us take some numbers. So let us say there's an array. It is called T, and in that array, we store this time required to read the papers. All right. So let us say the first paper takes 2 hours to read, or maybe 2 days. And how can we read a paper in 2 hours? Let us say if the first paper takes 2 days to read, second one takes three days, then third one takes 4 days, fourth one takes 6 days, fifth one takes 2 days, and again sixth one takes 2 days. Okay. So now my task is to distribute these papers to the 3 students. All right. So distribute these papers to student 1, student 2, and student 3. What is my goal? Such that the maximum load on any student is minimized. I'll write it down. Max load means max workload. Right. So let us take one distribution and then let us understand what do we mean. So let us understand what we mean by max workload with the help of a distribution. Okay. So let us say I want to be more aesthetic, and I will sort of denote these tasks with boxes. Let us say this is the marker for student 1. This is the marker for student 2. This is the marker for student 3. And let us say I am assigning the second, let us say the first paper to student 1, and I denote it with a box. So the height of the box is indicating the length of time. So this paper takes 2 hours, so this box height is 2. Okay, so then the second paper comes and I give the second paper, which is having 3 days workload, to student 2. Third paper has workload of 4 days. I give it to student 3. So the height of the box is the amount of time required to read that paper. All right. And then the fourth paper comes. I see that, okay, S1 is least occupied. Therefore, I give the fourth paper, which takes 6 units of time, to student 1. Then I see next paper should go to student 3 because student 3 is least occupied among the 3. So I give it to student 2. Did I say something wrong? Let me repeat it. So student 2 gets this 5th paper because student 2 is least occupied at the time when 4 papers are already distributed. So the last paper will go to student 3 because at that time student 3 is least occupied. So if I have done this distribution, then the maximum load is on student 1 because he has to read 2 papers. 2 plus 6, he has to spend 8 hours or 8 days, whereas this person, second student, has to only spend 5 days. The student has to only spend 6 days. So the max load is on S1, and we wanted to minimize this load, and our algorithm. So let us say load on a person is so load on student 1 is L1, or let us say load on student I is denoted by Li. So what I want to maximize, what I want to minimize is the max load over all students. All right. Is the question clear?
So like in this case, the max load would always be equals to the maximum plus minimum value, maximum time plus minimum time to read a paper. I mean, this would be the upper bound of the max workload. If the number of the student, if the papers to be read are greater than the number of the students available.
Right. If there are only 2 papers, then one person will not get anything. It's the right observation. So it's a good observation. So I'll write down that observation. Observation is if. So this is number of, hash means the number of. If the number of papers, or I'll say tasks, is less than the number of students, or I'll say number of men. Okay, men is not right word. It's people. If number of tasks is already less than the number of people, then at least one person will not get anything, and everybody else will get a task. Then nobody gets more than a task. Gets more than one task. And number of people minus number of tasks. People don't get anything. People get 0 tasks. Is that fine?
Yes, and what about the second condition wherein the number of the task is greater than the number of the people available? So we can say something about the maximum workload at least.
So now, if it so happens that there are 100 tasks, let us say, and only 3 students, then what you said will not go through.
Yes, yes.
So one person may get multiple tasks.
Yes.
More than 2 tasks is also possible. So what should we do?
Start
So
distribute.
I could not hear you. Can you repeat?
Start distributing the task from the greatest one. First 6, then 4. Like.
Okay. What is the rationale behind that strategy?
So because after the first one is given, the greatest one are already distributed, and next lowest will be started to distribute. We'll start to distribute. Like first we'll give 6, 4, and 3. Then I'll give 2 to the lowest one.
Okay, let's do what you said. So what you are going to do is you'll start with the distribution by assigning the largest task to someone.
So what is objective function here? It is a summation of Li or what? Because the Li can always be made equals to 0 in every case if you do not assign any weight to or any task to one person.
Oh, I see. I made a mistake here. So the statement is saying that the max load should be minimized, but what I wrote here is incorrect. How I should write it?
So is this a summation of so that the summation of the load we want to
Yes.
minimize the summation of LIs wherein the every LI should be less than some
No,
quantity.
no, no. So the loads you have, so for example, in this figure, you have distributed the loads and the max load is 8. So maybe there was a better way of distributing the load so that the max load is less than 8. So I should write it properly. How I should write it mathematically? So I have to introduce some notation.
Because my point here is that the minimum value of Li can always be made 0
Yes,
because
yes.
there is, so I mean that's the point. Yeah.
Can we write it like this? Minimize Lj such that Lj is max Li.
Yes, min max kind of thing.
Minimize. What did you say? You said, let's repeat what you said. Minimize.
Minimize Lj
Okay.
such that Lj is maximum Li.
Yeah, so I have to write it more concisely. What is the minimum taken? So minimum is taken over all possible distributions. So for a specific distribution, no, let's do one thing. Let us say, we need one J, like you have said. So let us say sigma be the set of all possible distributions. Okay. Then by sigma, let's say L sub I sigma, L sub I super sigma, I denote the load on SI. Load on SI is under. Okay, not sigma. I have to introduce J under some distribution J, which is in sigma. Okay. Now, so what is J? J is one particular distribution. So sigma is all possible distributions. So J is one particular distribution. So for example, this is one particular distribution. That this 6 and 2 are on S1, 2 and 3 are on S2, and 2 and 3, 4 are on S3. So that is J. Now the load on student I under the distribution J, I am denoting it as L super J sub I. Okay. Then I will say that, okay, so for all possible distribution J, which is of course within sigma, I want to minimize the max load LJI over all the students. So I is what? I is a set of students. So in this case, let us say, to be more general, let us say that the number of students is denoted by M. So I have M students to distribute load. Okay, so this notation means the set 1 through N. Now this is precise statement. Does this look good?
Yes, yes.
Okay, so I don't know who suggested this, but whoever suggested this, do you think that this is a precise description?
Yes, sir. It is like effectively what they said.
Now you understand the question that what we want to do. And thanks for pointing out that there was a mistake in the mathematical description. But this English description was correct. There was no ambiguity there. Right. Yeah, so somebody was suggesting this strategy. Yeah, so somebody was suggesting the strategy that first we will assign the largest job. So we want to assign the largest job to any of these students, right?
Yes, sir.
So let us say I give this 6 length job to S1. 6 goes to S1. And then what do you do?
Then least assigned will be assigned the next greatest.
Okay,
Yeah.
so you are going to process the tasks in the decreasing order of their lengths.
Yes, sir.
Okay, so your first step 1 is sort T in decreasing order. And then exactly what I did, you are doing the same thing. That's what I understood.
Yes, sir. This will give minimum.
So let us say I write down the sorted order first. After we have sorted the way we have suggested, we have 6 followed by 4, followed by 3, and then 3 2s. So after 6, you are going to give 4 to one of the least loaded persons. Then you have 3, so 3 has to go to S3 because S3 so far didn't get anything, whereas others have got. Then 2 will go to whom? Again to S3, right?
Yes, sir.
All right. So it's basically the same thing you have done. You have tried to say that you want to maximize welfare. So whoever is least loaded, you give the next load to that person. You're basically maximizing welfare. And
Last two will go to S3.
Oh, I see. Because this guy is already, there's a picture of a problem. I should make it larger. Okay, so now what is the maximum load under this distribution? This one.
7.
Correct. So this is only 7. So this under this distribution, load, max load is only 7. So previously our max load was 8 here. All right. So can you do better?
In this case, no.
Somebody said no. I think Mr. Goel said no. Anybody thinks something can be done, something better in this case?
So I have a small point here that this problem to me seems to be a subset some kind of the thing and a combination of something, say subset sum and knapsack also. Yeah.
Yeah, quite similar. Quite similar. So both the problems that you have pointed out, it's a very good observation. So one problem is subset sum, and the other problem is knapsack. Both the problem happens to be NP hard. There is no hope of finding the optimal solution in polynomial time. So what do you think about the hardness of this problem? This assignment of tasks to the students. In general, let us say there are n tasks and m students.
So basically we have to find the subsets in such a way so that the sum of the cardinalities of the subsets is equal to the number of the task. One thing. So like here, S1 set comprises of only one element. Its cardinality is 1. For S2, it is 2. So the sum came out to be 3 plus 2, 5 plus 1 is equal to 6 is equal to the number of the task. So we have to find the, so like in this case, the number of the subsets is fixed. That is, we have to find 3 subsets, but then we have to minimize. We have to find the subsets in such a way so that the sum of the maximum sum of a subset is minimized. And so for getting the subset sum, we'll have to explore a large number of the possibilities, and that will make the problem computationally interactive.
You are right. So there is a reduction which you not see, which proves that this problem is NP hard, and so therefore no polynomial time algorithm can solve it, or no polynomial time algorithm to compute the optimal solution is expected. Right. So now we are in this domain that the need for an approximation algorithm is visible. So the last slide that we have seen in the previous session was asking the question that when do we need to approximate? And it turns out that right now we have an occasion that we should look for a solution which is an approximate solution. So although in this small example, this is the best one could do and find the optimal solution having max load 7. But in general, if there are n tasks and m students, it is not possible to find the optimal distribution that minimizes the max load. It is not possible to do so in polynomial time. Okay. So we have to design some algorithm which gives some solution. And then we have to argue that what is the quality of the solution. Now remember the train and flight case. So remember the train and flight case, that when I did not have 10,000 rupees or 8,000 rupees in my pocket, then I was forced to take the train, and it took 48 hours to reach Guwahati. And I was sure that, okay, my approx factor, my approximation ratio. Okay, I didn't say it that way that time. Let's do it that way only. So I said that we have a 48 by 3 is equal to 16 approximation. So we want to be able to say something like this, that okay, we have this algorithm which Suhas I think has suggested, that we will first sort the times in decreasing order, and then we will maximize welfare by giving the next task as at hand to the person who has the least load at that time. So first step is sorting, second step is welfare maximization. And then we have to argue that what is the approximation ratio we have achieved, that when compared to the optimal solution, which we have no hope of computing ever, how far off we are. How far off we are from the optimal, that is minimum max load. So this algorithm only we'll analyze. So this is the crux of approximation algorithms. So the algorithm is simple. One step sorting, the second step welfare maximization. So the crux is how shall we prove that we are not too far off from the optimal. So that process of proving the quality of the solution is called analysis. So we need to do this analysis. So far, so good.
Sir, I had a doubt.
Yes.
In order to comment on how far off we are from the optimal maximum load, we need to have some idea of the optimal, right?
Very good question. So I said that we have no hope of knowing what is the optimal. We do not know how to compute the optimal. So there is no way we can find the optimal, but we should know that the optimal is of some nature. We should have some idea. As he said, I will use that word, the idea about the optimal is necessary. So when I write capital OPT, it means the value of the optimal max load. So we need to know what is, so let us say you have been given an input, 100 students, 1000 tasks. Suppose your computer will be able to do it, but let us say the number is very high. The number is too high, 1 million tasks. This I don't know. Let us say 10 to the power 10 tasks. And I don't know, 10 to the power 5 students. And let us say that you have run the brute force algorithm, and that is going to take a very long time, and you do not have so much time to wait that how to assign tasks. Then you want to do some approximate job, but then you want to be satisfied. You want to be self-satisfied that you did not do a very bad job. To be able to do that, you should have some idea about what is the max load on a student if the optimal algorithm was implemented. If we had infinite time, if we had a lot of time with us, then we could run the optimal algorithm and that would give us this value of OPT. But we will not find it, but we should find what is called a lower bound on OPT. So that idea, that word idea, in our case is a lower bound on OPT. I will tell more about it, talk more about it. So first of all, appreciate that we are minimizing something. So we have a minimization problem at hand. We are minimizing the max load on any person or any student. So we have a minimization problem at hand. So so let's look at a practical real life minimization problem. I don't know. Let's think about it. So let us say I'm hooking up some real life example. So let us say a surgical procedure is to be carried out on a patient. All right, so this involves, it's unavoidable that some pain will be involved. So this will involve rendering some pain to the patient. Okay. Right. But we want to minimize the pain. We do not want the patient to be subjected to a lot of pain. Okay. So my goal is again a minimization. So minimize pain to the patient. So suppose we are in a hospital and some very nice procedure, let us say procedure. I mean, when I say procedure, it also includes the equipments that are available with the hospital and all these things. So there is some procedure, let us say procedure A is available in this hospital. But then the patient wants to know that how much pain it will cause me. So maybe the best procedure in the world is not there in this hospital. Maybe the best procedure is procedure OPT. The best procedure is procedure OPT. So then I want to know, the patient wants to know that, okay, I am ready to undergo this operation, this surgery under procedure A, but how much pain will it give me when compared to procedure OPT? Okay, so let us say procedure OPT is not even discovered. That is also possible. So medical science is always evolving. So better procedures are always being invented. So let us say we have no way to know how much pain procedure OPT will inflict. But I have some idea about procedure OPT. Then let us say I can make a statement like that because of the inherent nature of the operation, whatever is the best procedure in the world right now on this day or in the future to come is minimum going to inflict the pain of, let us say, 4 units. So that means I am saying that OPT is at least 4. That is what I'm saying. I'm saying that whatever with the OPT, I do not know what it is. maybe it is 1, 2, but because of existing knowledge I have about procedures, surgical procedures, medical science, I think that OPT is not going to be. What did I say? 1, 2, no. I'm saying OPT is at least 4, so maybe OPT is 5. Maybe OPT is 5, 6, 7. But I'm saying that there are some inherent limitations that cannot push OPT below 4. Okay. So if I can say that OPT is at least 4, and then I claim, then I somehow am able to show that my procedure gives pain 8, then the patient will be satisfied that he is getting at most 2-folds more pain. That is the approximation factor. All right. So the lower bound on OPT is a way of comparing our solution with the OPT. Does it make sense? So we have to compute a lower bound on OPT. That idea that Indranil is talking about OPT we must have. That is the lower bound on OPT. And then we will be able to argue this algorithm suggested by Suhas, that this algorithm, step 1 is sort in decreasing order, and then step 2 is welfare maximization, is going to be at most some factor, let's say, I don't know, 2 factor, or I don't know, some factor away, at most 2 factor away from the optimum. That means if the max load turns out to be 1000, then this algorithm will give at most 2000 load, not more than that. So that kind of thing we'll be able to claim mathematically. Means we should be able to claim mathematically. All right. So our goal is the following. Right now, our goal is the following. To show that this algorithm suggested by Suhas is, I don't know, some constant. Let us say 2 factor. I don't know. Maybe it's 2 factor. It's 2 factor away from OPT. That is our, that we have to analyze. We have to write a mathematical proof of that. Okay. So far, so good. Is it clear what is the goal, what we want to achieve? So I think
do we have,
yes, go ahead.
yeah, so do we have well-defined techniques to carry out this lower bound analysis kind of a thing, that howsoever hard we try, we can never ever get a solution, say, better than this kind of a thing? Like,
Exactly.
say, yeah.
We have such solutions. We have some ways to find a lower bound on OPT. For example, in this proof, we will say that, okay, whatever the optimal is at least some this much load. So this much load is unavoidable. We will be able to say such thing mathematically.
Okay.
So this is what we are going to see. It is 6:08 now. Let us take a break. Let us reconvene after 10 minutes. Let's say 6:08. Let's say 20 minutes. I mean 12 minutes. So 6:20 p.m. we shall resume, and we'll finish in another hour. Maybe by 7:30 we can finish. So resuming at 6:30 and finish at 7. Okay. So let's take a break, all of us, and we'll meet again at 6:20 p.m.